So when we're talking about the mechanisms of enzyme actions, one of the concepts that I would probably get the most questions about is when I start talking about the interactions between substrate and enzymes that happen outside of the active site. And that makes sense because pretty much so far every time that you've talked about enzymes in other classes, you've talked about how the substrate interacts at the active site, and that's what happens. But there are actually two other types of interactions that can happen between substrates and enzymes. One of them is when the substrate interacts at the allosteric site to regulate the enzyme. An example of this is ATP, which is a substrate of phosphofructokinase, also binds to the allosteric site at a low affinity to negatively regulate it, as we're going to talk a lot about when we talk about regulation of glycolysis. The other type of interaction outside of the active site is when an enzyme is dealing with a polymer that is actually often much longer than the enzyme itself. And so that's an interaction that's involved in positioning the substrate to make sure that the interaction happens in the right order. And so today I need to shorten a bicycle chain, and I was thinking about how that serves as a sort of imperfect analogy for one of the most common enzymes that we discuss when we discuss enzyme mechanics, and that's lysozyme, which, if you remember from our discussions of lysozyme, it's an enzyme that cleaves between the glycosidic bond between two of the sugars of peptidoglycan. So peptidoglycan is a long chain made up of two sugars that repeat over and over again, N-acetylglucosamine and N-acetylmuramic acid. Also, the N-acetylmuramic acid has side chains of amino acids branching off of that, but we're not going to worry about that here. We're just going to talk about the core. And lysozyme cleaves the glycosidic bond between an N-acetylmuramic acid and an N-acetylglucosamine. And we talk in class a lot about the mechanisms, what's going on at the active site. When there are positioning effects, there's increased reactivity, there's a nucleophilic attack that leads to hydrolysis of the bond and a temporary covalent bond between part of the chain and the active site, and then a further hydrolysis that ends up with free regeneration of the free enzyme and the cleaved product. And so today we're going to be thinking about what goes on elsewhere, what's going on outside of the active site. And so again, for my analogy for this, my enzyme in this case is this tool right here, which is a chain breaker tool, a bicycle chain breaker tool, and that's going to be my enzyme, and this bicycle chain is the peptidoglycan. And so if you can see into the chain breaker tool, right in the middle right here, there's a little curve, and there's a pin that goes up and down. And we can call that our active site. And the way this works is when the chain is put in there, the pin goes down, and bicycle chains are held together by pins holding different plates together. And so in this tool, the pin will go down from the tool in our pretend active site and bump into the pin that's holding the bike chain together and push it out of the way, separating the plates of the bike chain. Kind of like the enzyme activity leads to that nucleophilic attack, leads to hydrolysis that leads to separation of the sugars of peptidoglycan. And the chain is broken. And that's fine, and that works pretty well, but chains are long and they twist and they can take different shapes. And if my bike chain isn't perfectly aligned, when this pin comes down and interacts with the bike chain, instead of pushing out the pin holding the chain together, if it hits it at an angle, the pin in my tool gets broken and my tool is broken. So outside of what I'm calling the active site, this curving bit right here where the reaction happens, there are two other interaction points that hold the bike chain straight. So it's perfectly aligned so that as the pin comes down, I can break the chain and separate it into the two parts without damaging my tool. Similarly, in an enzyme like lysozyme, there are interactions outside of the active site that hold the chain in the right position so the peptidoglycan is held positioned properly so that the correct bonds are in the correct location for the active site interactions to occur in the right order. And so basically that's all that happens when we have these outside of the active site interactions. We have extra interactions that hold the chain right where it's supposed to be so that the active site bonds can form in the right way, and as they form in the right way, they can lead to hydrolysis of the bond between the N-acetylmuramic acid and N-acetylglucosamine, and can lead to the two different products separating as a result. And so because they were lined up perfectly, now we can separate these two parts and have two different products. And again, we do this because the polymer is much longer and much larger than the enzymes we need to hold it in place. I hope that makes things a little bit clearer. Thanks. Have a nice day.